Hello friends, welcome to engineering tutorial. Now as I said in my previous video related to efficiency and ripple factor of full wave rectifier, I will be discussing about the regulated power supply or the regulated DC power supply in the next video. So today we are going to discuss about the regulated DC power supply. Okay, so first the basic, what is a regulated DC power supply? So this is the basic definition. So it is a power supply which maintains a constant output voltage. Okay, a constant output voltage, a voltage at a certain constant level which does not change, which does not fluctuate like AC. It will remain constant, flatline, irrespective of the AC main fluctuations or variations in the load. Okay, that power supply which gives us a constant output, flatline output, DC output, irrespective of the AC supply that we get or any fluctuations in the load, is called as a regulated DC power supply. Now I already mentioned or discussed about the reason why we need a regulated DC power supply. We all know that the AC supply that we get in our homes in India is 230 volt and 50 hertz frequency. Okay, 230 volt peak and the frequency is 50 hertz. Now there are many electrical appliances which require DC voltage for their operation. If you operate them with AC directly, if you connect them to the AC supply directly, they will get damaged, they will get burnt out. Okay, the circuits will be damaged because they have a certain power rating, which the power which they can handle. So for that reason we need to have a power supply unit which gives us a constant output. Okay, that is called as a regulated DC power supply. So these circuits are generally inbuilt in these electrical appliances. They are inbuilt, they are already part of their internal circuitry. So whenever they are connected to any the AC supply mains directly, they get converted into the required DC level that can be handled by those appliances. So these regulated power supply circuits are generally a part of the electrical appliances which are operated with DC. So that is the reason why we need a regulated DC power supply. So it converts the 230 volt 50 hertz AC supply into a required DC level, be it 5 volt, be it 12 volt, be it 8 volt, be it 12 volt, be it 24 volt, whatever the requirement is, but it should be DC. Okay, so this is the block diagram of a DC regulated power supply circuit. Now first there is the AC supply block, we all know, which is the AC supply which we get 230 volt 50 hertz in India. Then we have is the diode rectifier, which is generally the full wave rectifier. Okay, we have already discussed about the full wave rectification process in detail, so you please see that video, the half wave rectifier, the two types of full wave rectifier, which is the center tapped and bridge type rectifier, then only you see this video, because we are here only going to discuss about the smoothing capacitor and the voltage regulator concept. We are not going to repeat this rectifier part because I have discussed it almost 3 times, in once in half wave rectifier and twice in the two types of full wave rectifiers, the center type and the bridge type rectifiers. I have already discussed in detail how the rectifier works and how we get a pulsating DC output. Okay, we get a pulsating DC output like this, a pulsating DC output. So only thing which we are going to discuss here is how we get a almost flatline DC from the pulsating DC or a smooth DC. For that the smoothing capacitor is used, and then we get a constant value of voltage used with the help of the voltage regulator. Only these two parts we will discuss in detail. These two things we have already discussed numerous times in my previous videos. So you please check out those videos, the rectifier videos. Okay, so this is the circuit diagram of a commonly used DC regulated power supply circuit. So here you know this is the bridge type rectifier, full wave bridge type rectifier. This circuit you are familiar with if you have seen the video related to rectifiers, the full wave bridge rectifier. If you have seen that video, then you will be familiar with this part of the circuit. I am not talking about this, I am only talking about this part. So here we have the step down transformer which converts the 230 volt AC into some lower value of AC, be it 12 volt or any other value. Then we have this bridge type rectifier circuit which gives us this pulsating DC output. How we get this pulsating DC, I have already discussed that. Now, how to get flat DC, means smooth DC, how we smooth this waveform, how we get a flat line. We will never get completely flat line, but almost flat line, almost smooth DC we will get. Okay, how we do that we will discuss here. So here you can see this smoothing capacitor here, which is connected in this between ground and this point where we get the output, this pulsating DC output. This smoothing capacitor is used. Now one of the characteristics of the smoothing capacitor is that the discharging time, okay, the discharging time or the time which the capacitor, this capacitor takes to discharge is very high as compared to its charging time. You know that the capacitor stores energy in the electrostatic field in terms of charge. So the discharging time will be very high as compared to the charging time. It means, in simple words, it will take a lot more of time to discharge as compared to the time it will take to charge. Okay, so it holds on to the voltage for a long period of time. It holds on to the charge that it has stored for a long period of time, which is the characteristic which will be utilized to get a flat line DC output. Then we have the resistance which is used here. Okay, then across this we have a Zener diode. Now I have not discussed about Zener diode, but it is a normal PN junction diode which is connected in reverse biased mode. Okay, as you can see here, this P type end is connected to ground and the N type end is connected to the positive end. So it is reverse bias connection. So here the breakdown region or the concept of PN junction diode breakdown and reverse bias will be utilized. Now I have already discussed in the PN junction diode voltage current characteristics that in the reverse bias mode of operation of a PN junction diode, when the breakdown voltage is reached, there is a sharp increase in the current through the reverse bias diode. Now this occurs due to this high energy or increase in the kinetic energy of the electrons, the minority electrons, and then they get sufficient energy to knock out other electrons by breaking the covalent bonds. So that leads to breakdown, which is called as Zener breakdown. So I will be discussing about the concept of Zener diode. Now for now you just understand that whenever the breakdown voltage is reached, it maintains a constant voltage across this, which will be the Zener voltage, which will be a particular value of voltage and it will remain constant. Okay, so here this is a Zener diode is a normal PN junction diode which is connected in reverse bias mode. When the voltage across this diode will exceed the breakdown voltage, which is called as Zener voltage, that particular value of voltage will remain, the breakdown voltage will remain constant across this, and that will be the output voltage that we will get. So this is the whole circuit of a DC regulated power supply. Okay, so this is the normal bridge type rectifier. The output here looks something like this, the full wave rectifier output, this output of the full wave rectifier, which is the pulsating DC output. Now when this output pulsating DC is fed to the capacitor, the smoothing capacitor, which is an electrolytic capacitor, it has one important characteristic, which is that its discharging time is very high as compared to its charging time. It means that it will take a lot more of time to discharge as compared to the time which is taken by it to charge itself. It means that it will hold on to the charge which is stored by it in the electrostatic field for a long period of time. Okay. Now this Zener diode is a normal PN junction diode which is connected in reverse bias mode. You can see that this P-type end is connected to ground, means a lower potential, and the N-type end is connected to the output of the smoothing capacitor, which will be a higher voltage, a positive voltage, which means that it is a reverse bias connection. Now from the PN junction diode voltage current characteristics, we have studied that in the reverse bias mode of operation, there will be a very negligible amount of current flowing due to the minority charge carriers. Now when the reverse voltage exceeds above the breakdown voltage, okay, there will be Zener breakdown or the breakdown in the PN junction diode, and it will maintain a constant voltage across it, where there will be a sharp increase in the current through it. Okay, a constant voltage will be maintained, which will be the constant DC voltage that we require. Okay, this is the output of the smoothing capacitor. As you can see that this is the pulsating DC. Okay, now from here consider this peak point. From here to this peak, this is the charging time interval of the capacitor. From this to this, during this duration, from here to this peak point, the capacitor charges itself. Well, there is an increase in the pulsating DC. From here, the peak to the bottom, there is a decrease in the voltage. During this period, the capacitor discharges. Okay, so this is the charging of the capacitor from here to this peak point. From here to here, the capacitor slowly discharges. There is the slow discharge. It means that it almost holds on to the peak value of the voltage. It almost holds on. It's not completely flat. Okay, you can see here that it's not completely flat. There is a slow discharge of the capacitor voltage. So this value here is almost equal to the peak value, almost equal. This is the negligible amount. Again, during the other cycle, the capacitor charges itself during this. Again, it slowly discharges the voltage during the negative cycle. So this process repeats itself for the subsequent waveforms of the pulsating DC output. So we get almost flat line output. You can see the concept here. The capacitor first charges itself from this duration to peak. Okay, from here to here, this point, the capacitor charges. When the negative this voltage decreases from peak to this point, during this period, the capacitor slowly discharges. Okay, it slowly discharges. It means that it almost holds on to this peak voltage, this value. It almost holds on to this voltage. Again, when the lower to upper transition it takes place, it charges itself normally, okay, which is marked by the dotted lines. But again, then from high to low transition takes place, it slowly discharges. It slowly discharges. So we almost get a flat line DC output. Now this pulsating DC is fed to the Zener diode, which gives us a constant output voltage. Now this is the conventional circuit diagram of a power supply circuit. Now in place of Zener diode, we can use IC voltage regulators. Nowadays, whenever you design a regulated power supply, basically for your final year projects, when you design the projects, mostly you require two voltage levels, 5 volt and 12 volt DC, to operate the various circuitry, be it a microcontroller, be it a DC motor, be it a relay, be it a buzzer, be it a LCD, or any other device. You require basically two voltage levels, 5 volt and 12 volt. Normally these two voltages are required. Now for that, instead of Zener diodes, we normally use IC voltage regulators or integrated circuit voltage regulators. Now there are two types of IC voltage regulators: fixed positive voltage regulators, which give us a positive DC output, and fixed negative voltage regulators which give us a negative voltage output. Now this is the pin configuration of a normal IC voltage regulator. Here this is the input, which is given as IN. Here the output of the smoothing capacitor or the electrolytic capacitor is given. This point is connected to ground, and here is the constant DC output that we get. Now this is the IC number, the type number, which depends on which configuration you are using for a particular output voltage. Now this is the table which denotes the various IC voltage regulators. The type number is specified here, and this is the output voltage that we get for a particular time. So as you see here, the 7-8 part is constant for the fixed positive voltage regulators. The 7-8 part is constant. The remaining two digits 05, 06, 08, 09, 12, 15, 18, 24, they denote the fixed positive voltage output, DC output. If it is 05, it means that we'll get plus 5 volt. If it's 06, we'll get plus 6 volt. If it's 08, we get plus 8 volt. If it's 09, we get plus 9 volt. 12 plus 12 volt. 15 plus 15 volt. 18 plus 18 volt. 24 plus 24 volt. It means that for these IC configurations or these IC numbers, 7-8 means that we will get positive output. 7-8 denotes that we will get positive output, and the remaining two digits 05, 06, 08, 09, 12, 15, 18, 24, they represent the positive DC value, the exact DC, exact magnitude of the positive voltage. Okay, 5 volt, 6 volt, 8 volt, 9 volt, 12 volt, 15 volt, 18 volt, 24. Normally this 5 volt and 12 volt voltage levels are commonly used for various purposes. Okay, next we have is the fixed negative voltage regulators. Here also the configurations are same, just the difference is that here 7-9 is common in all the IC numbers. 7-9 denotes that the voltage will be negative, okay, negative DC, and the remaining two digits denote the magnitude of the negative voltage. So we have 7905, which means negative 5 volt, 7905.2, which denotes negative 5.2 volt minus 5.2 volt, 7906, which is minus 6 volt, 7908, which is minus 8 volt, 7912, which is minus 12 volt, 7915, which is minus 15 volt, 7918, which is minus 18 volt, and 7924, which means minus 24 volt. So here 79 means negative, and the remaining two digits are the magnitude of the DC voltage, which is negative, of course. So here we have discussed the basic regulated DC power supply, the basic definition, why we require a DC power supply, because the various electrical appliances require DC power for their operation. Then we discussed about the block diagram of the DC regulated power supply, where the AC supply and rectifier concepts we have already covered in the previous videos. We discussed about the smoothing capacitor and the voltage regulator, which is the electrolytic capacitor with a high discharging time, and a Zener diode voltage regulator or a IC voltage regulator. So we discussed the circuit diagram and how the smoothing capacitor converts the pulsating DC output of the rectifier into almost flat DC. Then we discussed about the two types of IC voltage regulators, their pin configuration and the type numbers corresponding to the different values of the output voltage. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to electrical, electronics, instrumentation and communication engineering. Have a great day. Thank you very much.